is the following statement going to be true, that for all integers a, b, and c, if a divides b and a divides c, then a divides b² plus 2bc minus c². We've already proven the case where these are two additions, and this one's a subtraction and that one's an addition. Now we're going to look at whether it's true when this is an addition and that's a negative sign. So let's just use a quick example to verify that this is potentially going to be true. So let's use the simple example of 2 and 2, 2 and 4. The reason I'm using 2 and 2 and 2 and 4 so much is because they're easier to compute when it comes to powers and when it comes to so much multiplication. So we know that these are obviously true statements. If you don't know why, watch my previous videos. So let's then quickly ask ourselves, is it true that 2 divides 4 squared plus 2 times 4 times 2 plus 2, or actually, yeah, let me quickly flip around the 4 and the 2. So we can write this as 2 squared, there we go. And of course, this is going to be true. You can factor a 2 out of here and a 2 out of here. If you can't see why you can do that, let me quickly just more explicitly write this out. 2 times 2 plus 2 times 4 times 2 minus 4 times 4. Fantastic. Of course, you can take a 2 out of here, a 2 out of here, and 4s can be divided by 2, so we can take a 2 out of here as well. So this is the same as saying 2 is divisible by 2 times 2 plus 2 times 4 minus 2 times 4. Fantastic. Because we've now written the right-hand side as a multiple of what's on the left-hand side, this statement is probably going to be true. Let's just quickly compute what this would have been if we didn't try and go this bracket way. This would have been the same as saying 2 is divisible by negative 16. So we're going to say 4 plus 4 times 2 is 8, 8 times 2 is 16, minus 16. So this is minus 16, that's 16, that's 4. So it's the same as asking, does 2 divide 4? And that is in fact going to be true because 4 can be written as a multiple of 2, where 2 must be multiplied by an integer of 2. So what are we asking? So we already have this 2, which is this 2. So is this whatever is in the bracket equal to this huge bracket? Well, yeah, because 2 times 4 minus 2 times 4 is going to be 0, leaving us with just 2 times 2. So it's looking like this statement is probably true. Let's go ahead and try and prove it. So this is a for all statement, which means that we prove for all statements by starting with the word let. What do we let? We let a, b, and c be integers such that a divides b and a divides c and a cannot be 0. If you're not sure why this is true, plug in a divide by any number 2, a divide 7, a divide some random integer m, and show me that, hey, you can't really write this as 2 times 0 multiplied by some integer k, right? You can't have 2 be a multiple of 0. Or try and rearrange for that integer that it must be multiplied by, and you'll notice it'll be dividing by 0. Anyways, next we probably want to put this in some mathematical formula so we can actually use divisibility. So we can then say, then b can be written as a multiplied by, let's use f, and c can be a multiple of a, meaning c can be written as a multiplied by some integer, let's use I. And because we've now introduced f and I, we have to explicitly state f and I must be integers. So next, we probably want to check that this thing on the right can be written as a multiple of a, or it can be written as a multiplied by some huge thing in a bracket where whatever's in this bracket must be an integer. So let's go ahead and do that. So we could say, next, b² plus 2bc minus c² is going to be the same as asking af² plus 2 times af multiplied by AI minus AI squared. Fantastic. Now here you should immediately be able to factor out a 2. In the previous two examples, like I've mentioned at the beginning, I didn't do that. I expanded the brackets, or I simply rewrote these as like A times F, A times F, things like something like that. But here I'm just going to assume you've watched all that. You can immediately see that you can, in fact, factor a 2 out of an A out of all of this, not a 2. So we can then say this is the same as saying A multiplied by AF squared plus 2FAI minus AI squared. Fantastic. Oh, and we want to close the bracket. So now we've shown what we wanted to show. This can be written as A multiplied by some huge bracket. The only thing that's left for you to understand is that everything here is going to add up and subtract into one huge, or just not huge, just one integer, whatever it is, big, small, normal, whatever integer. This is going to be an integer. So we just have to now explicitly state that, where what's in this bracket, AF squared plus 2AFI minus AI squared is in fact an integer. So because, or no, let's write this as a separate sentence for our conclusion. So we can say, in conclusion, b squared minus or plus 2b, I didn't miss that minus anywhere, yeah, okay, 2bc minus c squared is equal to a multiplied by af squared plus 2afi minus ai squared. Then, or in conclusion, so b squared plus 2bc minus c squared is a multiple of a, so it's true a divides b squared plus 2bc minus c squared. Fantastic. We have now proven that this statement up here is in fact going to be true for all integers a, b, and c.